Hi everyone, we're starting section 4C, expansion with radicals, from your textbook, the MYP4 book. So what we're going to be looking at today is, rather than doing addition and subtraction, which we did in the last lesson of radicals, what we're going to be looking at is the multiplication, or expansion with radicals. So if we go back and take a look at all the different forms of expansion that we've looked at so far, which we did in the previous chapter, we had the distributive property was the first type of expansion that we looked at with the distributive property. So that meant that we had A multiplied by B and A times C, so that everything outside of the parentheses would be multiplied by what's inside the parentheses, so that you would get AB plus AC. Now, if we were looking at two binomials being multiplied together, then that would mean that we would use FOIL, and that means that we would have A plus B times C plus D, and that would give us AC plus AD plus BC plus BD. And if we looked at the third situation where we had two identical binomials, then we would see that, yes, we could use FOIL, or we could use that shortcut method, which said that we would square the first. So we would square the first term, and we would square the last term. So that would be square the first term is A squared, square the last term, that would be plus B squared in this case, and then we would find the product of AB and then multiply that by 2, so that you would get plus 2AB. Okay, and then the very last form, and that was called perfect square expansion. And then the very last method that we learned was the difference of squares expansion, which was the easiest of all, because when we had two identical binomials except one was negative inside and the other one was positive, then all you had to do was square the first term and square the last. So square the first, square the last, and then you just had to put a minus in between. All right, so let's take a look at different solutions to these type of problems. Let's look at the first one that says expansion using the distributive property, so that we have 2 times the square root of 3 plus 4. So we have 2 multiplied by root 3, which equals 2 root 3, and 2 multiplied by 4, which gives us 8. There's absolutely nothing else that we can do here, in that the square root cannot be added to the 8 in any way, because the 8 does not have a root attached to it. This would be very similar to saying 2x plus 8. We can't add together 2x plus 8, and therefore we cannot add together 2 root 3 plus 8. All right, the next example gets a bit more complicated, and you have to just be very careful in multiplying everything through. So we have 2 root 3 times 3 root 2. Well, what that gives us is the 2 and the 3 on the outside of that square root get multiplied together, and that gives us 6. And what's underneath the square root gets multiplied together, which is 3 times 2. So that's going to be 6 root 6. The square root of 6 cannot be reduced any further. Then we do 2 root 3 times 6 root 5. So that means we've got a plus there, so we've got 2 times 6 is 12, and 3 times 5 is 15. Remember that you are multiplying together what's outside of the square roots together, and you are multiplying what's underneath the square roots together. Next one would be 4 root 2 times 3 root 2. So this one's a little bit trickier, because we've got 4 times 3 is 12, and that gives us the square root of 4. Root 2 times root 2. But root 2 times root 2, root 4 is really the same thing as saying 2. So this could be rewritten as 12 times 2. So in our simplification process here, we would have 6 root 6 plus 12 root 15 plus 24, because 12 times 2 is 24. And then our very last one that we would multiply together would be 4 times 6 is 24. I'll put that up here. Is 24. And then root 2 times root 5 gives us root 10. So that we have plus 24 root 10. Now, because all of these, or rather none of these, can be reduced down any further, then what we will have is everything just left the way it is. I can't bring root 6 or root 15 or root 10 down to the same root, and therefore nothing else can be collected. So we don't have any like radicals to collect, and therefore we just leave the solution the way it is. All right. The next example is using perfect squares, and with perfect squares we've got 2 plus root 3 all squared. So following the rules, we square the first term, which is 4, and we square the last term. Root 3 times root 3 gives us 3. I now do 2 times root 3, which is 2 root 3, and then that gets multiplied by 2. So that we end up with 4 plus 4 root 3 plus 3, and that ends up giving us 4 plus 3, collecting our like terms, which is 7, plus 4 root 3. We're finished. Okay, and then the very last example is one with difference of squares, and the one with the difference of squares just says to square the first. Root 3 squared is just 3, and then 2 squared is just 4, but there's a minus in between, so that's going to go to 3 minus 4, which equals -1. And we're done. All right, all we're going to spend the rest of this time now doing is just going over more examples. So let's expand and simplify, for example, root 5 times 6. Well, that'll give us 6 root 5. That'll give us 6 root 5. And if I have root 5 times root 5, that means it's just your answer going to be 5. Or root 5 times root 5 gives us root 25, which when simplified is 5. Let's take a look at the next one. Negative root 7 times 2 root 7. Well, root 7 times root 7 would give me 7, and that would get multiplied by -2. So that would go to -14 is the first one. And then negative root 7 times 4 gives us -4 root 7. Okay, so going over that just again for the first time, so that we have negative root 7 times negative root 7 times 2 root 7 would be -2 root 49, if we want to look at it that way. Okay, and then it would be minus 4 root 7. Now the square root of 49 is 7, so it would go to -2 times 7 minus 4 root 7. And again, that gives us the same answer as on the left-hand side, which is -14 minus 4 root 7. It's doing exactly the same thing, except I multiplied actually what was under the square roots and showed it as being root 49, which then goes to 7. Okay. Next page we have is we've got a difference of squares here. So because we've got a difference of squares, we've got 2 plus root 3 times 2 minus root 3. Remember that what we always want to look for is to see what the pattern is. What kind of expansion are we looking at? So I see that I have 2 identical binomials. One is positive, the other one is negative. It's a difference of squares. So all I do is I square the first and I square the last, which gives me 2 squared is 4, root 3 squared is 3, 4 minus 3 equals 1. And if I do the next one, well, again, I analyze or I look at my question, and I see that there is really nothing in either of those 2 binomials that matches. They're certainly not identical binomials in any way, so we're just going to use FOIL here in this example. So we'll do root 2 times 3 gives us 3 root 2, and we always put the whole number in the front. Okay, so if I have root 2 times 3, I'm not going to do root 2 times 3. It's going to be 3 root 2. Okay, that is not going to be accepted above here. Root 2 times root 2 gives me 2, and it's a minus, so it's minus 2. And then plus 1, or positive 1 times 3 gives me positive 3. And then 1 times negative root 2 gives me negative root 2. Now I look to see if there are any common factors or anything that's not common factors, but I'm looking to see if there's anything common that we can bring together. So I have 3 root 2 minus 1 root 2, which gives me 2 root 2, and then negative 2 plus 3 gives me plus 1, and I'm done. All right, the next one, we seem to have, again, taking a look at it, analyze what the question is giving you. So try to figure out, is it FOIL? Is it a difference of squares? Is it perfect squares? Is it just a distribution? And because I look at root 3 plus root 5 all squared, I see that it is a perfect square. So that I will square the first. So this allows me to square the first. So I get 3. Root 3 times root 3 is squared, gives me 3. I square the last. Root 5 times root 5 is 5, plus 5 here. And then I do root 3 times root 5 gives me root 15. But I have to multiply that by 2, so it's 2 times root 15, which gives me 2 root 15. And there's a plus, because everything is plus here. Now all I do is I collect like terms, and I say 5 plus 3 is 8, plus 2 root 15. And root 15 can't be broken down any further, because there are no perfect squares that break this down any further. Now let's look at the next one. The next one is still a perfect square, but it gets a little more complicated. So we're going to square the first. 2 root 5 times 2 root 5 will give us 4 root 25. But 4 root 25 is the same thing as saying 4 times 5. And then if I square the last, I have 6 times 6 is 36, positive 36. So we've got 20. So we've got 20 here, and then plus 36. And now we have to take all the middle terms here, everything that's inside the binomial, and multiply it together. So I have 6 times 2 is 12 root 5. So I have 12 root 5, but that must get multiplied by 2. So it goes to 20 plus 24 root 5 plus 36. And now 20 plus 36 gives me 56, so that we have 24 root 5 plus 56. And I always keep forgetting to put my equal sign aligned nicely. Okay, let's look at the next one. We've got expand and simplify. That is, again, a difference of squares. So I'm going to square the first. And squaring the first here means that I do 2 times 2 is 4, times root 2, which goes to 2. So 4 times 2 goes to 8. And then square the last, minus 1. And therefore, my answer goes to 7. All right, let's do another one where we have, again, another perfect square. Now again, there's nothing stopping you from foiling it. We can always foil 3 minus 2 root 2 times 3 minus 2 root 2 if it gets too complicated or too difficult for you to do it the other way, at least for now, until you get comfortable with it. But if I'll just do it the way I prefer for you to do it. So square the first, it's 9. Square the last, 2 root 2 times 2 root 2 will give me 4 times 2, which is positive 8. And then 3 times negative 2 root 2 will give me negative 6 root 2. Multiplied by 2 will give me negative 12 root 2. And so my answer will go to 9 plus 8 is 17 minus 12 root 2. Again, I would have gotten exactly the same answer if I had just FOILed it. Okay, I could have FOILed, or I could have used perfect squares. So I'll leave that for you if you want to just try using FOIL. I'll leave that for you to figure out. Okay, and the very last question that I wanted to go over is this last question here. And the last question here basically says, well, if I've got root 63 times root 81 and I have to expand that, do I really want to expand root 63 times root, like multiply out root 63 times root 81 to get the square root of 5,102, and then have to simplify it, that would be too time consuming. Okay? But the one thing that you could do is this, is that you could break down the 63 and the 81 into their simplest forms already, just before even doing the multiplication. So what that means is I could break down 63 into root 9 times root 7, and I could break down root 81 into 9, because the square root of 81 is 9. Now, the square root of 9 is 3. So if I do 3 times the square root of 7 times 9, I'm going to multiply together the whole numbers, the ones that have no square root on them, 9 times 3, which is 27, and I'll get 27 root 3. If I were to calculate now and try to see if 27 times root 3 actually gave me 5,103, I would do 27 times 27 and then times 3, and that should give me as an answer 5,103, and that would be under the square root, and that would work out. So actually breaking down the radical before you multiply it makes it easier for you to actually multiply through, so you don't have to then break down large numbers. Okay, I'm done. Your work will be on PowerSchool. So far it will be exercise 4C from the MYP4 textbook, but there can be more. See you next time.